In this video, we're going to talk about what a function is and how we can tell if a graph or any other representation of a set of data represents a function. So let's start off by defining a function so we know what we're looking for. So a function is a relationship and it's a relationship between a set of inputs and outputs, where each input is related to exactly one output. And that exactly one is really important for a function. I know wording of math definitions can be kind of confusing sometimes, so let's put it into something we're more familiar with seeing. So a function is a relationship between a set of x's and y's, where each x is related to exactly one y value. So a common definition that you're probably familiar with hearing about a function is that there are no repeating x values in that set of data. Y values can repeat all day. Doesn't matter how many times a y value shows up in a set of data. It's the x values that we're worried about. X values are what we call independent variables, so they're what are controlling the function or controlling the situation or controlling the data. So in order for it to be a function, only one of those can show up in each set of data. So it's okay for us to have three fives as y values, but we cannot have three fives as x values also. So when we're looking at a set of data, we use the vertical line test, or sorry, specifically when we're looking at the graph of a set of data, we use the vertical line test. Hopefully that's something you have heard before. We use that vertical line test to determine if the data represents a function. If the graph represents a function, then the vertical line will touch only one x at a time, or only one point at a time. There will never be 2 points that are stacked on top of each other on a graph like this. Something like this, where we have 2 points above or below each other, this would not represent a function because when we use our vertical line test, that line cuts through both points at once. So that would not be a function. We would need those points to be staggered a little bit, something like that, so that when we do draw our vertical line, it's only touching one of those points at a time. Just a little example there. So let's look at these 4 graphs here below, and we're going to use that vertical line test. And I'm just going to draw a bunch of vertical lines going left and right across the graph, and if at any time it touches more than one point at a time, it's not a function. So let's zoom in here on this first one. We just have a random set of data here. This is not a continuous graph. So if we draw our vertical lines, we can see right off the bat there at the very beginning, we have 2 points sitting on that one line. I'm just going to erase that line so you can see how those points are stacked right on top of each other. So when we draw that vertical line, it touches both of them at once. So this is not a function. And I'm just going to give a reason why I'm going to justify my answer here. So not a function, because the vertical line test, I'm just going to abbreviate that as VLT so I don't have to write it out every time, touches 2 points at once. Alright, so let's try that again on our second graph here. Again, we just have a random set of data here, but we can see that they are making a line. And as we draw our vertical lines across the graph, we never have more than one point touching one of those vertical lines. So this one is a function. Oops. And again, I'm going to justify because the vertical line test only touches one point at a time. You could also say that there are no repeating x values. So to just kind of clarify what I mean by that, over here, if we were to write these out as ordered pairs, this point is the point 1, 5, and this point is the point 1, 4. And we can see they have the same x value, so that would be a repeating x value. That's why it's not a function. If we were to write each of these points out as ordered pairs, they all have different x values as we go across the graph from left to right. So no repeating x's, this is a function. And we'll look at some continuous graphs now, so not just a random set of points, but a full graph. Here we've got a graph of a circle. If we draw that vertical line anywhere on the graph, we can see there are actually an infinite amount of places where our graph is touching 2 points at once, where that vertical line is touching 2 points at once. I've just drawn 4 vertical lines. They're not very straight there, but you can see that as it cuts through that circle, it's touching a point at the top of the circle and at the bottom of the circle. So we have repeating x values all the way across that circle. So this one is not a function. And I'm going to justify it again, but this I'm just going to say there are repeating x values. That's the same thing as saying it's touching 2 points at once using the vertical line test. All right, and then one more. We have a cubic graph here. And as we draw some vertical lines across our graph, now each of these lines I've drawn, you can see it's only touching 1 point at a time. On the edges, it does look like over here on the ends that line is becoming really straight, and that it might be becoming a straight line where we do have some x values stacked on top of each other. However, that line is changing very slowly, which is why it starts to look like a straight line. However, it is very slightly slanted, so it is continuing out just a little bit, very slowly. It is not a straight line, therefore there are no repeating x values happening here. So because there are no repeating x values, this is a function. And again, I'm going to justify no repeating x values. Okay, so that vertical line test is a really quick visual way for us to determine if a graph represents a function without actually having to look at the ordered pairs and identify the actual x values. We can just look to see, are there 2 points stacked on top of each other? If so, not a function. If they're all spread out where they don't overlap at all, then we do have a function. So a graph is just one way to represent a function or a set of data. There are 4 other ways we can represent data. One way being an equation. We're probably familiar with that connection between an equation and a graph, so that's probably pretty obvious. Then we have ordered pairs, which we know are all the points that are on a graph. And then we could have a table, which is just an organization of a bunch of ordered pairs. And then lastly, we have a mapping diagram. And this is probably the representation that we're all least familiar with. You probably haven't seen it outside of Algebra 1, but again, it's just a way to organize ordered pairs without repeating numbers the way we might repeat numbers in a table. So we're going to look at each of these forms and determine how we know if each form tells us that we have a function or not. So we have been given a set of data in this first example. We've been given 5 ordered pairs here. So if we're just looking at ordered pairs and determining if we have a function or not, all we're looking at are the x values. We don't care about the y values. I talked about it at the beginning of this. Y values can repeat as much as they want to. It doesn't matter if we have a repetition of y values. We only care about the x's. So I'm going to go through and highlight all the x values because that's all we need to pay attention to. As long as each of those are different numbers, then we have a function. And if we look at our x's, we have -1, 0, 2, 4, and 5. Those are all different numbers, so this does represent a function. Now we're going to take those ordered pairs and we're going to organize them into a table. And a table, again, you're probably pretty familiar with tables. They just have a column for the x values, they have a column for the y values, and an ordered pair is connected in a row in that table. You might also see tables horizontally where we have rows instead. So we have a row for x's and a row for y's where the ordered pairs are stacked on top of each other. They're the same thing, just two ways to orient that table. So let's plug those ordered pairs into the table. We have the point -1, 4. Let me write the right number there. -1, 4. 0, 5. 2, -6. 4, 3. And 5, -6. Again, just like with the ordered pairs, if we were given a table and asked to determine if it were a function, we are just looking at the x value. So we're just looking at this column of x's. We're looking to see, are there any numbers that repeat in that column? As long as they're all different, then we know we have a function. In a table, the order of your points isn't really important. A lot of times you'll see the points ordered by x value, so probably least to greatest with the smallest x value at the top, the biggest x value at the bottom, but they don't really necessarily have to be in that order. A lot of times that's how you'll get it from a calculator, so that just ends up being how we write it down on a piece of paper. Now when we move to mapping diagrams, it is very important that we sort our numbers from least to greatest. So I'm just going to make a little note under the table here. We sort our numbers from least to greatest. And we do not repeat numbers. So even if a number shows up more than once, whether it's an x or a y value, we only write it once in our diagram here. So we don't repeat numbers. Okay, so just like a table, a mapping diagram sorts the numbers by x and y. So that bubble on the left is our x, the bubble on the right represents our y values. And in each bubble, we're going to write the x values from least to greatest, and we're going to write the y values from least to greatest. So this time the ordered pairs are not necessarily just directly across from each other. They could be diagonal. The order is more important with a mapping diagram. So x's were given to us in order, luckily, so we'll just go ahead and write those out. We don't have any repeating x's, so we'll write each of them once. And then we'll do the same thing with the y's. Now we do need to make sure we put them in order, so we're going to start with the smallest number, which would be -6. Now -6 does show up twice in our ordered pairs, but we only write it once in the mapping diagram. Then we'll move to 3, then 4, then 5. Now in a mapping diagram, the way we communicate which numbers are pairs is through a series of arrows. So we're going to draw an arrow from the x to the y to indicate an ordered pair. So our first ordered pair is 1, 4. So I'm going to draw an arrow from -1 to +4. And that's how I know that -1, 4 is an ordered pair. Then I'll connect the next point, so 0, 5, we'll draw an arrow from 0 to 5. It's always from x to y, never the other way. And then we'll go to -6. Then we'll have 4, 3. And then lastly, 5, -6. So if you notice, there are two arrows pointing to -6 in the y column, and that's okay. In order to determine if a mapping diagram represents a function, we look at the number of arrows that are coming from the x values. So we're looking at these arrows right here in the x column. That's what tells us if we have a function or not. As long as there's only one arrow coming from each of the x values, so -1 has one arrow coming from it, 0 has one arrow coming from it, 2 has one arrow coming from it, 4 has one arrow, 5 has one arrow. As long as they each only have one arrow, then we have a function. However, if we had two arrows coming from one x value, so I'm just going to draw in an example here. If we had a second arrow coming from 5 going to a different y value, now do you see how there are two arrows coming from that 5? We have one going up to -6 and then straight across to 5. When we have more than one arrow coming from an x value, it is no longer a function. So you're looking to see how many arrows, well, you're really just looking for one arrow from each x. That's how you know if you have a function. If there's more than one arrow, not a function. Redraw. Okay, and then our last representation, which is probably what we're most familiar with, is a graph. So we just take our points and we plot them. Remember, ordered pairs are x, then y. So we'll go -1 on the x, +4 on the y, 0, 5, 2, -6, which is just a little off our graph there, 4, 3, and then 5, -6 again, just a little off our graph. That's okay. And then just like we talked about up above, to determine if a graph is a function, we use the vertical line test. And if we ran some vertical lines across our graph, we would see that we're not repeating any x values as we move across. All right, so those are our different set of representations, a way to represent a set of data. Whether it's a function or not, each of these forms can be used to organize data. And then specifically, we're looking at those x values to determine if we have a function. So we only want each x value to show up once if it's a function. So let's try one more example here. All right, this time we were given an equation, and then we need to fill out a table, the ordered pairs, and then our graph. Because we have an equation here, we get to do a little bit of choosing to fill in the table and the ordered pairs and then the graph. When you're given an equation, you get to choose the x values. You'll take those x values and you'll plug them into the equation to solve for x, or to solve for y. It doesn't matter what x values you choose. When you are deciding on x values, especially if you're going to have to graph your data, I would take a look at the x values that you're given on the x-axis. If you're limited the way we are between -5 and +5, I'm not going to want to choose -7 as an x value because that's not going to fit on my graph. I'm not going to want to choose 10 as an x value because that, again, is not going to fit on my graph. So I would suggest keeping it on your graph, so choosing any of the x values that sit on the x-axis that you're given. Outside of that, it's up to you. You might also pay attention to the equation you're given. For example, where we're plugging in x, we're having to multiply that number by 1/3. And if we're multiplying by 1/3, that really means we're dividing by 3. So if we want to make this easy on ourselves, we're going to choose numbers that can divide by 3 evenly. You don't have to do that. You're welcome to plug in numbers that don't divide by 3 evenly. That just means you're going to have a fraction as your answer. Fractions are okay. Fractions are our friends. But if we want to make it easy, and there's no problem in doing that, choose numbers that are going to give you whole numbers as answers. So if I am choosing some x values, I always like to start with 0 because 0 is usually a pretty nice number to plug in, especially if you're having to multiply by a fraction, because when we plug in 0, 1/3 times 0 plus 2, anything times 0 is 0, right? So 0 plus 2 gives us a 2 value for the y. Then let's choose another x value. So this time I'm going to choose something that is divisible by 3. So I'm going to choose a +3. We're going to plug it in for x. So 1/3 of 3, or 3 divided by 3, is just 1. And then we'll add 2. So 1 plus 2 gives us a positive 3 for our y value. Now, we can choose numbers that are going to sit just off of our graph. You don't exactly have to be bound by the x-axis like I was talking about before, but it is nice. And you definitely don't want to choose numbers that are too far off of that graph. So I'm going to choose 6. It's just barely off the graph, so that's still going to be pretty easy for us to graph, and it's also a number divisible by 3. So 1/3 of 6, or 6 divided by 3, is 2, plus 2 gives us 4 as a y value. Now I'm going to go the opposite direction, and I'm going to plug in -3. So 1/3 times -3, or -3 divided by 3 is -1 plus 2. -1 plus 2 is a positive 1. And then just as an example, I do want you to see plugging in a number that is not divisible by 3. So for example, if we plugged in positive, or let's do -1. So 1/3 times -1 plus 2. So 1/3 times -1, or -1 divided by 3, is just -1/3 plus 2. Now remember that when you add and subtract fractions, you do need to have common denominators. So to make 2/1 a denominator of 3, we're just going to multiply by 3. So that turns into 6/3. So then -1 plus 6 gives us -5/3. And if we thought about that as a decimal, which is how it's going to be easier for us to graph, that'll be -1 and 2/3, which is -1.6 repeating. So it is definitely possible to plug in numbers that are not divisible by 3. It just means you're going to end up with a fraction or a decimal as your answer, and that's okay. All right, now we're going to take these ordered pairs, and we're going to take our table and we're going to write them as ordered pairs. So we have the ordered pair 0, 2, then 3, 3, then 6, 4, then -3, 1, and then lastly we had -1. I'm just going to write it as the decimal since we're going to be graphing it, -1.6 repeating. And then we'll finish out by plotting these points. So we have 0, 2. Again, remember, ordered pairs are x then y. And then we said 6, 4 is just barely off our graph. So we can still go ahead and plot that. And then -1 and -1 point. Oh, that was a positive. I wrote that incorrectly. My fault. Sorry if that was confusing, where that negative came from. I can understand why. Let's make that smaller. That all should have been a positive 5/3, or a positive 1.6 repeating. So about right there. And then we can just draw our line through those points. And we do want to draw a line this time because this was an equation. This is a continuous set of data. I could have chosen any x values. I just happened to choose these 5 x values to plot, but you could have chosen anything, so points could have shown up anywhere on that line. So we are going to draw a line to connect those points, even though we didn't do that on previous examples because we were just given ordered pairs. We weren't given an equation. All right, so just to recap, a function means we do not have any repeating x values. So on a graph, we use the vertical line test to determine if there are any repeating x values, if we have any points stacked on top of each other. In a table, we look at the x values. We're looking to see if they're all different. In ordered pairs, again, we're just looking at the x values. Sometimes it's helpful to circle those or highlight them. We need them all to be different. In a mapping diagram, we're looking to see, is there only one arrow coming from each x? Then we have a function.